Okay, so today we're going to be looking at approximating small changes. So to begin, we're going to suppose that we have some function that might look something like this. And on that function, we have perhaps a point P and a point Q. And so what we want to know is we want to start thinking about what would be the gradient of a line that joins these 2 points. Imagining that that's a straight line. Okay, well maybe let's think about that in terms of what we already understand from junior mathematics. The gradient of a line between 2 points is m equals, well, if P is the point x1, y1, and Q is the point x2, y2, we can consider the formula to find the gradient between these 2 points to be m equals y2 minus y1 divided by x2 minus x1. Oops, x1. Or another way of thinking about it is we can look at, well, let's have a look at this x distance here and say, well, that's actually the change in x from sort of here, this point, all the way across to this point here. That's our change in x. And similarly, we could also say that this distance here is the change in y. And that distance there is, this is actually the y coordinate y2 here, and this is the y coordinate y1 here. So we can sort of mark that in. That's y2 up here and y1, and so you can see that distance here, delta y, will be the change in y over the change in x. And I think that's okay for you to understand. So maybe we can rewrite that formula to say that equals, if we've got space, the change in y over the change in x. Okay, well, now what we want to do is let's think about this distance here from x to y, sorry, from P to Q. Let's think about, what if we shrunk Q, and what if we moved it down to here, here, and eventually all the way down to where a point where Q is arbitrarily close to P. Okay, well, now we can do what we did before and draw a line between P and Q, and you can see that as Q becomes closer and closer to P, we actually have a situation where the line between them approximates the gradient of the curve at that line. And what I mean by that is, the line that I draw between point P and point Q, here and here, this line approximates the actual derivative of this curve at this point. So what we can actually say then is, let's make this a little bit out of the way. Well, you know how we were talking before about how this distance here, another way we can describe this distance being delta x, or the change in x. Well, we can say that as our point P and point Q become closer and closer together, i.e. our delta x goes to 0, as our change in x approaches 0, so the change in y divided by the change in x, which is what we agreed before was a way to say that the gradient of the line between P and Q, that actually approaches the instantaneous rate of change, in other words, the derivative at that point. And when I say that point, what point do I mean? Well, I mean at this point P. So we're talking about now where Q is so close to P now that it's come all the way down from here, all the way down to right down here, very, very close to P. And so now they are, and yet they are still slightly separate. Well, now the gradient, delta y divided by delta x, can be approximating the gradient, the derivative. Okay, well, the next thing we can do then is say that delta y divided by delta x approximates the derivative. And now if we multiply both sides by this delta x here, we'll have an expression that will just be in terms of delta y. So let's go ahead and do that. Delta y is approximately equal to dy dx times, that's a little time sign, delta x. Or in other words, I just made those a bit smaller. Delta y can be approximated by the derivative of our function times a small change in x. Okay, well, how can we use this mathematically? Right now it's a little bit of an abstract concept, so what kind of problems does this apply to? Well, for example, we could look at problems of this type could include things like changing the radius of a sphere, and then asking ourselves, well, how does this affect and change the volume of the sphere? That's a good one. So in terms of measurement, another one can be two-dimensional shapes. I've given you an example of three-dimensional shapes, and we'll actually look at a few different other examples that are non-measurement related. So it's a way of finding out. So if my radius of my sphere was 10 centimeters and now it's 12 centimeters, well, how is my volume of my sphere going to change? And so you might say, oh, well, I can just use my formula to find out, and that'll give me an exact answer, not an approximate answer. And you're right. However, we can't always use the formula in all cases, and so this is how this gives us a good approximation at times. So, with that being said, let's try an example. Example 1. Okay, so Jan, she has a ruler, and it's out by 1%. That means no matter what she measures, she's always going to have an answer that's wrong by 1%. Okay, so she goes and measures something. What does she measure? She measures the side of a cube. And then calculates the volume. So the question that we want to find out is, what is Jan's approximate error in volume? Okay, so what this question's asking is it's asking us to find the approximate error in Jan's volume. It hasn't actually given us any values within the question of what the actual cube's going to be. It's just said that she's out by 1%. So we've got to find out, okay, how are we going to measure her approximate error in volume? Well, the first thing I think we can do is let's remind ourselves of our formula for approximating small change. The change in y is approximately, it's the dot above and below my equal sign to show approximately, equal to dy dx, or otherwise known as the derivative, times the change in x. Okay, well, let's maybe apply this formula to our case. Now the change in y, the y is a dependent variable, and so the dependent variable is going to be the volume. Okay, the thing that she's measuring is independent, and that's the side of our cube. So we want to know what is going to be the change in volume, in our case, the error in volume, or the change in volume, and that's going to be approximately equal to the derivative, the change in volume with respect to the side length, and then multiply that by whatever the change in the side length is. That's the formula we want to fill out. Well, we need to find the constituent parts of that. So firstly we can think of, well, what is going to be the change in our side length? Well, the change in our side length is 1%. So as in, if I measure accurately, 100% accurately, the side length to be 10 centimeters. Oh, for ease sake, let's go 100 centimeters. If it's 100 centimeters, then Jan's result could have been anywhere between 99 to 101 centimeters. So she's out by 1%. So we've got that. We can put that straight into our formula. Now we just need dV ds. Well, for that, we're going to need some calculus. So, the rule for the volume of a cube I might just draw my cube. There's my cube. Vol cube is equal to the side cubed. Okay? Well, what's our side length that we can use for this? Well, we don't actually know our side length. So we'll just keep it as s cubed, and to differentiate that, bring the 3 down the front, multiplied by s, and drop the power by 1. That's our change in our volume with respect to the side. Now that can go into our formula. 3s squared times 1%. Okay. Now, the question's asking us what is the approximate error in volume. Well, we don't know what the side is, so we can't include the side, but what we do know is that there are 3 lots of 1% in volume, and therefore the approximate error will be 3%. So what we've actually found is that from an approximate error of only 1% in measuring the side of our cube, so we've only picked out a little 1% little slot out of there. Actually, what we found is that turns into 3% error in the overall volume of the cube.